we'll continue with the presentations. We're going to present one of my favorite projects in senior design this year. It's a tricycle for the visually impaired. I think this is a team that has done a tremendous job. It's including mechanical and electrical. It's a mixed relationship for this presentation. Team 8, are you guys ready to start?
Yes.
Ready as we'll ever be.
Okay.
Go ahead.
All right, hello, and thank you for being here. My name is Mike Lyman.
I'm David Chapman.
I'm Juliana Ocampo.
I'm Sasha Fisher.
And we're here to present to you Tricycle Cycling as part of the Senior Design Project for University of Texas Tyler. The project is named after Tiresias, who is the blind prophet of Apollo.
Our presentation consists of the design, fabrication, assembly, and testing of a tricycle for the blind or visually impaired. The purpose of creating our system is to allow the visually impaired to experience the freedom of riding a tricycle with as little assistance as possible. We took a closer look at the blind and visually impaired community and found that there are 39 million people in the world who are blind or visually impaired. To be considered legally blind, a person's vision is 20/200 or worse, which means that what a legally blind person sees at 20 feet, the average person can see at 200 feet. Visually impaired encounter many environmental, social, and technological challenges throughout their everyday life. We then conducted some background research to determine what has already been done and found that the University of New Hampshire had created a tricycle for the visually impaired using an array of ultrasonic sensors and buzzers that will alert the rider when there's an object right in front of them. However, it does not tell the rider how to navigate around the object. It just merely tells them that it's there.
The other project which we continued was a previous project from last year, and it was the flexibility and freedom system, and because of this, we pretty much had to go from the ground up and rethink it, and that includes the sensor placement, the process control, and also the track design and the material we use for the track.
The image behind me is just a drawing that's going to show us what elements we changed that were on the bike so that we could assemble the whole thing. We're going to talk about these in a second. We're going to talk about the gear down reduction. It's an element that we visited, as well as the control box, the IR housing, which holds the IR sensors that it works on, the motor housing, which holds the haptic feedback motors, and also in the front of the bike is the ultrasonic housing.
This is our design tree, which highlights just some of the engineering decisions we made along the way. It basically shows our thought processes, our iterations, and our design choices that led us to our final design.
So this is a system that really hasn't ever been tested or ridden extensively before. So in order to make sure that the bike wasn't moving at a speed that we thought was inappropriate speed for users to learn on, we decided to gear down the bike. We chose to go from a 36-tooth drive gear to a 25-tooth drive gear. Mostly that was because of availability. It seemed like on the market, 25 teeth was the lowest we could get with the same pitch diameter. So we went with that. It was pretty easily accessible on the market. An additional benefit to gearing down the speed was also that the rider had a little bit more torque than what the bike originally came with, which meant that they didn't have to pedal as hard. What you're seeing now is just a couple of the calculations that we did to try to figure out whether or not we were going to increase or decrease the chain length. Overall, we decided through calculations that we would remove 6 links. The bike didn't originally come in a way that you could remove the links, so we had to remove one of the links and replace it with a master link.
For our control box, we chose a weatherproof control box to hold all of our electrical components. Originally, the bike came in with a basket in the back. We removed the basket, we used that available space to place our control box. Also, we added a plexiglass platform when we chose a plexiglass platform because it's cost efficient, impact resistant, and doesn't oxidize. This is one of the example of the electrical schematics that details our circuit in our control box. For our processor, we chose a Raspberry Pi 3 Module B+, because it's easy to work with, open source, and also can be programmed using Python that has good documentation, and it's robust enough to allow future complex functionality for future improvements. Also, we added a motor shield to our Raspberry Pi to protect the main board from surge and also to give us an external power for our haptic feedback.
So for object detection, we chose an ultrasonic sensor. This is the model HC-SR04. It has about a 4-meter range. It can detect anything about 4 meters in front of you. We chose this because it was, inexpensive, easy to obtain, worked with the Raspberry Pi, and had some coding libraries which ultimately we had to rewrite, but were still compatible when we did write our own with the Raspberry Pi. Once that sensor detects an object in front of the bike, it sends a signal to the buzzer. The buzzer goes off and alerts the rider as to the object in front.
In order to attach the ultrasonic housing, a custom piece had to be designed and fabricated at a PLA, and the placement of the housing allowed for the sensor to stay in line with the user's trajectory.
This is the IR sensor we chose, and this is an active object detector. And basically how this works is the white LED sends out a beam, and depending on the intensity that the black one receives back, it will trigger the delta and alert the user there's an object. And part of the reason we chose this is because we can select the material that absorbs IR more than the surrounding environment. And we could also adjust the sensitivity with its potentiometer. Now this is just an example of some of the simulations we did through our process, because at first we thought we were going to have a rigid IR housing, but I needed to see if we needed to redesign it, so I needed to do an FEA. However, these are not statically loaded or force-bearing members, so standard FEA, you can't do it. So I did the most likely scenario of an impact condition and found that under some of the impact simulations that the piece did experience plastic deformation and would have to be replaced. So in order to facilitate, but basically in order to dissipate that force, we added a hinge, and then this is an example of some of the mathematical calculations we did in order to make sure our models are accurate. And basically, in order to make those calculations, I had to make a number of assumptions. One, that the housing was perfectly rigid. I assumed it was a cantilever beam, and that its temperature was under the glassing transition phase of this thermoplastic. And we found that under the FEA, we found around a 1/16 of an inch of displacement for about a gram or two rock, which, small pebble, kinda. And then our displacement for that same mass was 0.0784 inches, which gives us about a 26% difference. But considering these, the system is nonlinear, and you have to do an iterative process to do like an FEA analysis, we figured that this was good enough for the purposes of, to move on from this. And this is after we added the hinge, we needed a rapid return. So at first we thought we were going to go with a hinge, not a hinge, but a spring, but springs oscillate. And we need this to return to 0 as quick as possible. So we chose a magnet because once it pops back down, it'll stay right there, and it's the perfect solution for our purposes. This is an example of some of the drawings that we did to ensure that the pieces were manufactured correctly. And this is the IR housing that we finished, and as you see, it's on the bike.
For the haptic feedback, we chose 2 DC motors that were placed inside each of the handles to allow the rider to adjust their direction. In order to reduce the vibrational noise between the handles, we had to use damping material to dissipate the vibrations to travel through the metals, so the rider doesn't get any false pulses from one handle to the other. This is an example of the manufacturing specifications on the motors. According to our research done at MIT, a typical bike can experience a vibration on the handle clustered around 60 hertz. Our handles were estimated our motors were estimated to vibrate at 100 hertz. Because we calculated the margin of error to be 20 hertz, we needed to get feedback on the motors to determine what voltage they should run at. For power, since this is a moving object, we decided to place a self-charging station inside our control box. This charging station includes a 2-watt solar panel, a DC-DC converter, a power booster that are connected together, and they continuously charge the 3.7 volts, 2500 milliamp hour lithium-ion battery that will power up our whole system.
All right, so for the material track considerations, one of the things we were taking a look at for the track was whether or not it was going to be durable, reusable, transportable, inexpensive, and non-marking. In the previous iteration of this, from last year's bike, they used paper. That didn't work for a number of different reasons. One of the reasons was that it ended up tearing itself up as they were going over the bike. The other reason was that in order for it to kind of stay down, they were taping the paper a lot, it was tearing. For this reason, we chose a fabric. It's a basic cotton material. It's inexpensive. You can pick it up at Walmart. Very easy to obtain. Pretty cost effective. And like David was saying before, the IR sensor, the infrared light gets absorbed more by the black material, especially the color, but also the material itself, which means that we can use the object detection as more of a line detection at a greater distance. In order to appropriately test the bike, we contacted the Lighthouse of Houston organization. We took the bike over there and got some results and also some feedback. What you're about to watch next are a series of videos of us actually doing that. The first video is just a calibration that we had to go through. I'll explain the logic as it happens through in the video. Okay, so that's just a short video. We did both sides, but if you could see if there, I'm putting the track underneath the sensor before we laid it down and then pulling it back away. Originally, we had thought that a right trip on the right sensor should buzz the right handle, telling you that the line is on the right and it should turn away. But we found that that's not very intuitive, because as you feel something buzzing on your right hand, your intuition is to turn that way, which meant that they were turning towards the line instead of away from it. So we ended up switching the motor wiring so that we could flip that. I don't know if I can push this back, but the right sensor buzzes the left buzzer. And that's the right sensor, and she's turning left because the right handle is buzzing. That's the logic that we had to use in implementing this system. So this is a video of Jennifer riding the bike. One thing to note here, some of the things that we hadn't considered about visually impaired people riding the bike is what their feedback would be like, which is part of the reason why we did this. So she's going to overcorrect a little bit in using this bike, and you'll see that here in a second. So she's coming forward. We don't have sound on this video. She's going to get a buzz from the right sensor there, and she's going to make that left turn, but she keeps turning left instead of staying straight, which means she's going across the other thing. We'll talk about that a little bit more in a second. Here's a video of John riding the bike. Now he's going through a turn here. He has, I think, a little bit more experience with the bikes, so we're going to watch this video real quick. Now, he's getting that buzz on that right sensor, which means he's turning left. And he's doing it very subtly, and as a result, he stays in the lanes. At this point, he gets no information, so there's no buzz, and he goes through. At the end of that, we have him stop. So this is just a little bit of the feedback here that we were getting, and this is Jennifer talking about the motors.
You know what I'm saying? Like, maybe you can get it, like, fire. Makes sense. Yeah. You don't want it slide if you're trying to get away and not crash. You know that's so. Yeah. Makes sense. Yeah.
Okay, so before we talk about economic feasibility, I don't know if you could hear her clearly because the auditorium here is different than our presentation, but she's basically saying what we kind of confirmed, which was that the vibrations of the handles were kind of getting lost in the vibrations of the bike. In the original thing we were talking about the hertz of that. So
we conducted economic feasibility to see if our system was viable, feasible, and cost effective. We found that our prototype cost was going to be $41,320, which includes the cost of the parts and the cost of the billable hours for research, design, fabrication, assembly, and testing. And for our mass production cost, cost to be $807. Now you can see our prototype cost is a little high, but as you can see, it only accounts for 5.12% of the final overall cost. We did some market research to see what was out there currently, and found that even if we double our MSRP to $1,615, as you can see, electric bikes run at about $3,100, and special need bikes can start from anywhere from $1,600. So we thought our pricing would be reasonable. We also have copies out there of our assembly operations and maintenance manual, along with our parts manual.
And finally, I just want to say that we've demonstrated that through the scientific method and the engineering processes that we've learned here, that we've proved that something that was previously thought impossible, that we can make it possible.
At this point, we'd like to give a special thanks to Dr. Garcia, who's helped us in kind of guidance on how to organize things along the way. We'd also like to give a special thanks to the Lighthouse Organization of Houston, especially Melissa and John, who are sitting in the second row to our right. We thank you for being good test subjects.
For being here today.
Questions?
Yes, sir.
Yeah, do you recharge the battery with, the riding of the bicycle?
No, I wish I wanted to do that. No, we have a solar panel. And also we have a DC-DC converter and a power booster that will take any kind of light and will charge the lithium-ion battery and will power up our pipe.
Does the signal work well inside?
Yes, sir, it does. It turns on inside, and it was perfect, actually.
Yeah, funny enough, when we were testing this, it was a little low in power, so we used our cell phone light for the on the front of it just to get enough power so we can make sure it turns on, and it worked.
And apparently, it charges pretty quickly because we had it on our cell phone. We had no power. We had it on our cell phone for like 5-7 minutes, and we were good for 15 minutes. So.
What happens if you get completely out of power,
Sorry, continue.
It will need to be on power.
Right. So it's important to realize that when you're setting up the bike, when whoever is riding the bike, they're still going to need some assistance in getting this bike to work. So in the operation manual, one of the things it lists is make sure that it's fully charged. There's a light on there that you can tell inside the box. One of the other things is just to make sure, like it goes through a checklist of things that you're supposed to make sure you do. So while it does give somebody the freedom to kind of make their own choices on the track, you do still have to have some assistance in order to use this product.
So as the video was shown with Jennifer when he was checking the sensors, that's one of the things that needs to be done before the blind person can just go and on the track. You need to check the sensors, make sure that the haptic feedback works, make sure everything works in here and is charged, and also our power booster has a light that tells you if it's fully charged or it's not fully charged, so you can double check that as well.
Anyone?
I wanted to follow up on the same question because my question was in the same area but in a different way. Maybe I missed it. Why aren't you using the power by the rider to power your system? Is there a reason that prevents you from doing that?
Well, so there are dynamos that are out there that attach to the axle that would allow you to charge it while you were riding it. Ultimately, we chose not to do that. First of all, because of cost. Second of all, because of space. Any self-made dynamo we could have used or any generator we could have created may not fit in the form factor that we really needed down here. Ultimately, we thought that it would be a little bit easier on manufacturing and also a little bit easier on parts in order to just go with the solar charging station.
I think it's an expansion area or an area to explore for two reasons. One, cell powers are governed by the ability of light, which is not a factor for the visually impaired, so they don't care, they might ride at night or something.
Right.
So, and you're governed by a lot of things. But everything that has to do with self-containment is moving in the direction of self-power and energy harvesting. And there isn't more than an energy out of a human that you can harvest. So I think there is room there similar questions of sensors, for example. We're using ultrasonic in the front, we're using infrared at the back, ultrasonic is detecting objects, infrared is detecting the light. Why the mix of sensors? Why not infrared all the way? They do both our jobs.
Well, that's a good point. I mean, we could easily have chose both. I mean, but they're around the same cost. And the way we have this program is this almost works like they have this is essentially a digital sensor, and this is more analog because like how we have this programmed is as it goes closer, it beeps more. So it's a continuous signal rather than discrete time signatures. Those.
But I guess DEC and ADC is not a problem these days. You can
No, of course.
I'm looking at the manufacturability factor, and the fact that I can buy one box of bolts that works for everything instead of 3 boxes of different bolt sizes is a cost factor in manufacturing.
Yeah, that's a fair point.
That's something that also is worth expanding on. You have to have a line to track to make sure that.
That is correct. Yes, you do have to have a line. So in the presentation, the line is set up as bumpers. We tested a line directly underneath, and it turned out that because of the restraints of the bike, just the bike, size and the spacing of the wheels, the track would have had to been very thin. It only gives you a moment of feedback, in contrast to the bumpers. One of the things that you could see on the video that we, were trying to kind of deal with was, as you go through the turn, we had to take a look, or should take a look in the future with making the turn lanes slightly thicker, because as you drive over it, you lose signal. So that's an area of improvement that we need to work on.
I would say next team take it over, get rid of the whole line. I want to drive it.
Oh yeah, that's actually one of the areas that we have focused on is there's primarily 2 ways that we've researched to do that. One way is,
the first way we thought of, we specifically use a Raspberry Pi because we could use the Raspberry Pi camera for an open source to have an invisible track, just to input the track into the camera and connects it to the motors, and that's how it worked without a track. And there is another way.
Yeah, the other way I researched was like real-time kinetic GNSS guidance, but those tend to be really expensive. But the advantage, the problem with GPS is like everyone thinks, well, you can make a wireless track out of GPS. Well, you can't put a rider on and say, hey, by the way, you're good plus or minus 9 feet. So we were going to go with real-time kinetic, but it's like $700, which is like more than almost the entire system out of the box. And there's also a way you could do it. I've researched you can use multiple GPS sensors that have a high signal, like 10 hertz or so, and basically they sample each other. You program basically throw out outliers with statistics stuff.
Once we started getting into the weeds with some of the other options, it was very apparent that we did not have the computer science skills in order to implement some of these solutions. The Raspberry Pi camera would have been fantastic. I would have loved to have taken a whole year to learn how to do the image processing. You were in the class, but only 2nd semester.
I'm in class right now.
So that was something we definitely wanted to do in the beginning. We bought the camera as part of the prototyping. It wasn't that expensive.
We've done a lot of research. We've done some coding as well in order to get it to work, but we weren't able.
Actually, I interrupt you because you're going you're very enthusiastic about it, and you have done research, and it's obvious. But my questions are more exploratory, if you have noticed. Why this, not that? If I was going to do it quickly off the top of my head, I identify the sensors, I'll try to get rid of the line, I'll use something different, and I'll use the GPS to locate my rider, because they're at the end of the day visually impaired, and I need to know where they are. If I click on my phone, hey John, where are you? Oh, I can see you, I know where you are.
Well, the kind of the workaround for that was, it's not on the system right now, but this is a spot, because I was thinking well, how can we have a camera on the system? And out of the box, the wireless cameras are pretty expensive, the ones that would work with a Pi. So I was like, well, why don't everyone has a cell phone, we could strap a cell phone on here and it works. You just basically FaceTime, and it's a cheap workaround that we could use, and everyone has a cell phone, strap it on there, and we get live video feed wherever you are, just with the phone.
But I know I'm hugging the floor, so one last question. The haptic feedback. So what you have in there is a motor or some sort of an actuator that you may veer off, or if you give it a signal, it's going to vibrate and give them some sort of a feeling to it.
That's correct.
Okay. Is that only to correct direction?
That is currently only to correct.
To correct action, yes.
Yes,
But-
there are,
Sorry, I was going to say, actually, it's kind of additional to what you're saying is part of the reason why it's amazing to have the Lighthouse to help us, because they brought up something that we would have never thought of. Is that, like, for instance, the number one cause of blindness in people is diabetes, and one of the things associated with diabetes is neuropathy. So you get, basically means you're less sensitive.
sensitivity.
Yeah. So
Which we did not think about, when we were going in, it was only something we realized after we had talked to them.
There's definitely a lot of physiological benefits on top of having physical activity with visual impaired on this. And the possibilities are endless. I want to say this is a very good piece of work, but I do see 2 more teams on it to get it to the market. Still, there is a lot of work. Doesn't take away from your credit though. Very good job.
Thank you.
Thank you.
Thank you, sir.
Do you know what Ross robotic operating system is? Did this come up during all this?
I know KUKA, but I do not know Ross.
Okay, so Ross is a robotic operating system that's made for communication infrastructure for sensors. You can build a virtual path in there. You can take a 3D scan of your environment, build a path, drop this thing in there, drop your Raspberry Pi on there, and it can look for the virtual line in the robotic system, in the virtual environment, cross-reference it. If you put your compass heading with the GPS and run it through a Kalman filter, you'll get it down to 1 centimeter.
Really?
Yes.
oh wow.
This is what we do on our swarm bots.
Do you know what the, I can
It's
ask
called
questions.
Ross
We'll
robotic
talk about it
operating
later.
system. Look this up, okay? Work on the turtle bot. You can push it on here.
Yeah, that's amazing because I was researching so much for GPS because I thought we kind of went in a different direction. So you thought visual learning, and I was like, well, I like GPS, but I just could not find sensors accurate enough that were cheap enough that would work,
Something they're not considering.
and I had not considered that.
Yeah, you have to cross-reference it and push it through a Kalman so you can clean it.
Okay,
Alright.
thanks.
Yeah.
And I think this idea gives basically an entrance to maybe a joint project for senior design next year with Jack and ourselves to get this thing into
Yeah,
real estate.
it's a really good project.
It's a
It's a
really
good
good
idea. You guys have done a creative job with it. So.
Any other questions from?